Welcome to the video lecture for Chapter 5, Section 4, and this is included with the Chapter 1 concepts and topics that we're going to be covering within this group of lectures. So the objective for this one is we're going to solve polynomial inequalities, and we're also going to solve rational inequalities. And so the first one is polynomial inequalities. So when we're going to go ahead and solve this one, which is x plus 3 times x minus 1 squared is greater than 0 by graphing. And what we're going to do is we're going to actually graph the function f of x is equal to x plus 3 times x minus 1 squared. So when you graph the function and determine the intervals of x for which the graph is above the x-axis, the values of x result in other words, in f of x being positive. So we can see here from the graph, we can see that the function itself is greater than 0 for the values between -3 and 1. And so, or also greater than 1. And so the solution set for this would be all numbers x such that -3 is less than x, less than 1, or x is greater than 1. Now using interval notation, we would have -3 parentheses, -3, 1, union 1 to positive infinity. So what we ignore would be anything that would make the function less than 0 or equal to 0. So how do we solve a polynomial inequality algebraically? So we're going to solve x to the fourth is greater than x algebraically, and then we're going to go ahead and graph the solution set. So the first step is write the inequality. So the polynomial expression f is on the left side and 0 is on the right side. So we end up with x to the fourth minus x is greater than 0. So this inequality is equivalent to the one that we wish to solve. Step 2, determine the real zeros. So find the zeros, the real zeros of f of x is equal to x to the fourth minus x by solving the equation x to the fourth minus x is equal to 0. So here we can see we go ahead and factor out an x, and then we factor out x cubed minus 1. That is a difference of cubes. And so we have x times x minus 1 times x squared plus x plus 1 is equal to 0. So we're going to set each of the factors equal to 0. And so we get x is equal to 0, x is equal to 1. Now, the last factor, x squared plus x plus 1 equals 0, has no real solutions. So therefore, we're not going to consider that. And in step 3, we're going to use the zeros found in step 2 to divide the real number line into intervals. So we're going to divide the number line into 0, negative infinity to 0, 0 to 1, and then 1 to positive infinity. And then what's going to happen at this step is we're going to choose a test point in each one of the intervals. So for this test point is -1. For this one, we choose 1/2. And then for this interval, we're going to choose 2. And then we're going to find the value of the function for each test point that we chose. So the first one, we get 2, which is a positive. The second one, between 0 and 1, we get a negative. And in the last interval, the test point 2, we get a positive. So since we want to know where f of x is positive, in other words, conclude where the function f of x is greater than 0 for all numbers x, for which x is less than 0 and x is greater than 1, because the original inequality is strict. Numbers x that satisfy the equation x to the fourth is equal to x are not solutions. The solutions of the inequality then in essence becomes negative infinity to 0, union 1 to positive infinity. So the nice thing about this is the following. If it's positive for one test point, and in any point within this interval is positive for the entire interval. So we chose -1. We could have easily chosen -2, -10, -100, -1000. Doesn't really matter. You would have gotten a positive value if it's positive. Same thing with this interval. We could have chosen 3, 10, 100, 1,000, a million. It would have been positive. So when we choose a test point, it's either positive or negative for every single value within the test point. Now, same thing here. It's negative for every single value in the interval of 0 to 1. So therefore, when we don't choose this because we only want where the function is greater than 0. So the next one, we're going to solve rational inequalities. So solve a rational inequality using the graph. So we have x minus 1 divided by x squared minus 4 is greater than or equal to 0. We're going to end up graphing the function r of x is equal to x minus 1 divided by x squared minus 4. And so when we graph and determine the intervals of x, such that the graph is above or on the x-axis, the values of x result in r of x being positive or 0. So we graph the function, in example 1 in the textbook, and this is what we got. Now from the graph, we can see that the function r of x is greater than or equal to 0 for values between -2 is less than x, and x is less than or equal to 1, or x is greater than 2. So the solution set then would be, using interval notation, would be -2 to 1, open and half open interval, union 2 to infinity with an open interval, or closed interval, sorry. And so how to solve a rational inequality algebraically? So here we have this inequality. We're going to solve this algebraically, and then we're going to go ahead and graph the solution set. So the first thing we do is we move all the values over to the left side, so we have 0 on the right. We want to combine this into just one fraction, so we multiply -3 by x squared plus 4x plus 4 divided by x squared plus 4x plus 4, and then we combine like terms. We end up with x minus 3 divided by x plus 2 squared is less than or equal to 0. So step 2, we're going to determine the 0. So the 0 of f of x is when is 3, because 3 minus 3 is 0. 0 over any value expression is equal to 0. And also the function is undefined when x is equal to -2. So we're going to use this information to create our intervals. And the intervals that we're going to create is -∞ to -2, -2 to 3, and 3 to infinity. Remember, it's 0 when x is equal to 3, and it's undefined when x is equal to -2. So those are the 2 points that we use to create our intervals. Since we have 2 solutions, or 2 possible solutions, we have 3 intervals. And then in step 4, we have all of our intervals. We're going to choose a test point within each interval. So for the first one, we choose -3, we get a negative value. For the second one, we choose 0, and we get a negative value. For the last one, we choose 4, and we get a positive value. Since we want to know where the function is negative or 0, we conclude that f of x is less than or equal to 0 for all numbers for which x is less than -2, or -2 is less than x less than or equal to 3. So notice that we do not include -2 in the solution because -2 is not in the domain of the function. So the solution set for the original inequality then would be, using interval notation, -∞ -2 union 2, and then the half open interval -2, 3. And since this is positive, we ignore that. And that's the end of section 5.4. Thank you.